classification of elements and periodicity in properties. In our lower standard, we studied that elements are basic constituent of all matters. In 1800, only 31 elements were known, but by 1865, this number becomes almost double. Means the number of elements discovered by 1865 almost become double, went up to 63. At present, more than 110 elements are known. Out of them, the recently discovered elements are not naturally occurring but are synthetic, artificial, or they are known as man-made element, prepared during the nuclear fission reaction. Efforts are still going on to synthesize more such artificial elements. With such large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. For man-made or synthetic element, one of the reason is that their abundance is very less, and because of that reason also, it is very difficult to study their individual chemistry. At this stage, scientists felt the need of some simple method, or I can say a systematic way, to organize their knowledge of the study of properties of various elements and their compounds. This necessity led to the classification of various elements into groups. Classification of elements into groups and development of periodic law and periodic table are the consequences of systematizing the knowledge gained during experimental observation. Development of the periodic law and periodic table is because of efforts of scientists to organize the knowledge of the chemistry or to organize the experimental result obtained for the various elements. It is the everyday support for the students, and it provides a brief organization of whole chemistry or one kind of handy tool to understand, or I can say that to correlate the properties of various elements with respect to each other. It is remarkable demonstration of the fact that chemical elements are not a random cluster of entities, but it display some kind of similarity or trends, or they lie together in some families. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law also. We will also learn how the periodic classification follows a logical consequence of the electronic configuration. Means how periodic classification is related with the electronic configuration of an element, that also we will understand over here, and all this periodic classification is directly or indirectly related with the electronic configuration of an element, that we will realize in this topic or in this chapter. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the element. In our this first video, during our discussion of historical development of the periodic table, we will mainly talk about this 4 points, that is Dobereiner's Triads, A.E.B. the Chancourtois Cylindrical Table, Newland's Law of Octaves, and Lothar-Meyer Arrangement of the element. In historical development, we will talk about this 4 mainly. We will start with Dobereiner Triads. In case of Dobereiner Triads, the first attempt to classify the element was made by the German chemist John Dobereiner in early 1800. In 1829, he noted a similarity among the physical and chemical properties of several group of 3 elements, various group of 3 elements. he identified certain group of 3 elements where he noticed some kind of similarities in their property. This group of 3 elements were called Dobereiner triads, and his relationship is called law of triads. In each case, he noticed that the atomic weight of the middle element was approximately the arithmetic mean of the other 2 elements present in that triad. Also, the properties of the middle element were also in between the other 2 elements. Since concept of the law of triads seemed to work only for a few elements, it was rejected by considering it as a mere coincidence, and therefore this was an initial effort which didn't sustain for a long time. Some of the elements of this triads are lithium, sodium, potassium, where sodium is a middle element, so atomic weight of the sodium is arithmetic mean or nearby the arithmetic mean of the lithium and potassium atomic weight. As well as I can say that in case of this type of element, property of the sodium is in between the property of the lithium and potassium. Same thing we can say that strontium atomic weight is in between or arithmetic mean of the calcium and beryllium atomic weight, as well as property of the strontium is in between the property of calcium and beryllium. Sorry, barium, not beryllium, barium. Second is A.E.B. the Chancourtois cylindrical table. In case of A.E.B. the Chancourtois cylindrical table, he classified the element. In that case, he prepared a cylindrical table by drawing a helix at an angle of 45 degrees. He arranged the unknown element in an increasing order of atomic weight in helix, and he observed that elements whose atomic weight differ from each other by 16 or multiple of 16 fell along the same perpendicular line and showed nearly the same properties. So he prepared a cylindrical table by drawing a helix at an angle of 45 degrees, and in that case he found that element whose atomic weight is 16 multiple or differ from each other by 16 or multiple of 16 fell along the same perpendicular line and shows the similarity in the property. Then the third attempt was made by the Newlands, which is known as the Newland's law of octaves. The English chemist John Alexander Newland proposed a law of octaves in which he arranged the lighter element in increasing order of their atomic weight and found that every 8th element had properties similar to the first element. Every 8th element has properties similar to the first element. For example, sodium is 8th element from the lithium. Let me see. This is the arrangement of the element in an increasing order of their atomic weight, and this is lithium first, beryllium second, boron third, carbon fourth, nitrogen fifth, oxygen sixth, fluorine seventh, and 8th element will be the sodium. So property of the lithium is similar to the sodium. Again from the sodium, if you count first, second, third, fourth, fifth, sixth, seventh, then 8th element will be the potassium. So property of the potassium is also similar to the lithium and sodium. Same thing you can say for beryllium. If you start your calculation from beryllium, then this is first, second, third, fourth, fifth, sixth, seventh, eighth. Eighth is in magnesium. So property of the beryllium is similar to the magnesium, or magnesium is similar to the calcium. So based on that, after sodium, the next element is potassium. So all three have a similar property. In short, he found that every 8th element had properties similar to the first element. Similarly, we can explain for beryllium, magnesium, calcium. But this law of octaves seemed to be true only for the lighter elements having atomic weight up to 40 and for element having atomic number greater than 40, this was not obeyed perfectly. This law also became incorrect with the discovery of the noble gases, because after that the 8th element cannot have a similar property. The property of the 8th element were no longer similar to those of the first one, and therefore this law of octaves or Newland law of octave was also not found much more applicable for the classification of elements, and therefore this kind of another approach at that time was made by Lothar-Meyer, which is known as an Lothar-Meyer arrangement. In case of Lothar-Meyer arrangement, the periodic law as we know it today is because of two scientists, one Russian chemist Dmitry Mendeleev and second German scientist Lothar-Meyer. Both contributed significantly for the development of periodic table, and they were the first successful person who did a successful attempt to classify element or to organize the element at that time whatever available, and in that case both the scientists had worked independently and proposed that an arranging element in the increasing order of their atomic weight, similarities appear in physical and chemical properties after regular intervals. Lothar-Meyer studied and plotted the graph of physical properties such as atomic volume, melting point, boiling point, and various elements versus their atomic weight. He found that the element with similar properties have similar positions on the curve. He plotted this kind of the graph of atomic volume versus atomic weight. Then in that case, look, the all peak. All this peak are nothing but a lithium, sodium, potassium, rubidium, means they are alkali metal. If you look after alkali metal, the descending position of all the elements, then here magnesium, here calcium, here strontium, here barium, these are alkaline earth metal, means highly electropositive elements are on the peak. Less electropositive elements are on the descending position. Same way, if you look the ascending position, then fluorine and neon, chlorine and argon, bromine and krypton, iodine and xenon are fall on this position. Means electronegative elements are on the ascending positions. So based on this, the most strongly electropositive elements like alkali metals occupy the peak on the curve. He noticed this thing. At the same time, he noticed that the less strongly electropositive elements like alkaline earth metals, beryllium, magnesium, calcium, strontium, barium occupy the descending position on the curve. And look this, the peak is alkali metal, descending position is your alkaline earth metal. Same way, the most electronegative element, fluorine, chlorine, bromine occupy the ascending position on the curve. And look in the curve, this is the ascending positions where chlorine, this is a fluorine, this is chlorine, this is bromine, this is iodine are present in the ascending position. From the above graph, Lothar-Meyer concluded that the physical properties of element are periodic function of their atomic weights. On the basis of this, he arranged known element in a tabular form in order of their increasing atomic weight. Lothar-Meyer developed a table of element that closely resembles the modern periodic table. Lothar-Meyer table or tabular form of the classification is closely related with the modern periodic table, but even though very few people know about the Lothar-Meyer, reason is his work was not published before the work of the Dmitry Mendeleev published, and hence Mendeleev is generally credited for the development of the modern periodic table. Otherwise, the similar kind of the approach was made by the Lothar-Meyer, and he also prepared almost similar kind of the tabular form of the classification of element like Mendeleev proposed at that time. So this is about the historical development of the modern periodic table. So these are the four initial, I can say that attempts were made to classify the element, and then the first reasonably successful attempt was made by Mendeleev, and that is known as a Mendeleev periodic law and Mendeleev periodic table, which we will see in our next video.